So in this video I want to talk about graphing rational functions. Remember, rational functions are ratios of polynomials, and so we'll have variables in a denominator, and that's going to cause the graphs to do some interesting things. So suppose we are staring at a rational function. Let me give you an example. Okay, so the first thing I would suggest is that we factor the rational function. Factor the top and bottom, if you can. Okay? So then there's lots of things that are easy to extract from the rational expression. Okay? I'm going to make a list of them here, and they're all useful. Zeros, intercepts, x and y, asymptotes, I'll talk about what those are in a second, wholes, and long-range behavior. So often you will have technology, you will have software that can instantly make a graph for you of a rational function. However, there's lots of properties of the graph you can get really quickly with inspection. Okay, so I'm going to do an example right now. If for some reason you couldn't graph it, well, you didn't have a graphing calculator, for whatever reason, maybe you just wanted a quick inspection, get some quick information without graphing it. So zeros, okay, zeros, that has to do with x values that make the entire function be 0. So if we call this function f of x, then can you see that f of minus 1 is equal to 0? So then f of minus x equals minus 1 is a 0. And that's also a y-intercept, an x-intercept. All right. Now, to get the y-intercept, we plug in 0. And if we do that, we get, let's see, 0 plus 1 divided by 0 plus 2, 0 multiplied by 0 plus 3, that gives 1 over 6. All right. Now, and moving right along, an asymptote. So an asymptote is a line that a graph appears to be that in the long term it gets closer and closer to it, but it never quite reaches it. Okay? So why would this have an asymptote, and what exactly is the asymptote that it has? Well, actually this has a couple of asymptotes. Now, you might recall that you cannot divide by 0. Okay? So a rational function, the domain doesn't include x values that cause you to divide by 0. Now, as you get closer to those values that are not allowed, the function will spike. It'll either become a huge positive value or a big negative value. All right, so that's called a vertical asymptote. So for this one, we would say that, so the zeros are the 1, 0, x to the minus 1. The intercepts are minus 1, comma 0, as well as 0, comma 1/6. And so the asymptotes, we've got a vertical asymptote, x equal to minus 2 and x equal to minus 3. Okay, now we also have a horizontal asymptote. All right, horizontal asymptote means it's getting closer and closer as x gets huge, or it gets a big negative number. So looking at this rational expression, try plugging in bigger and bigger positive and negative numbers on your calculator. Like for example, 1,000 and negative 1,000, or 1,000,000 and negative 1,000,000. If you do that, you will see that you keep getting a smaller and smaller answer that never exactly reaches 0. So y equals 0. The x-axis itself is a asymptote. In this case, it's a horizontal asymptote. All right? By the way, notice what we just did to find the horizontal asymptote. We saw what the function was doing as x got very large in the positive or negative direction. Okay? That is also referred to as the long-range behavior. The behavior really far away from the origin, really far to the right or far to the left. So the way you could write it, let's do that before holes. You would say that as x approaches positive infinity, the function is approaching 0. And likewise, as x approaches negative infinity, in this case it's the same both ways, so the function is approaching 0. Okay, now a hole. A hole would be also other x values that are not in the domain. However, these are holes. These are not in the domain, not because you're dividing by 0, but because some joker forgot to reduce the fraction. Okay, so for example, looking at the original expression, suppose that I had x plus 5 on top and x plus 5 on bottom. All right, now typically you would simply cancel those out and move on and never think twice about that, right? However, if for some reason you weren't allowed to reduce and you had to graph what it would be before you reduced for some reason, then there would be a hole, in this case, at x equal to minus 5. Because the value, you'd have 0 on top and 0 on bottom, which is undefined. So I guess this is also a special case of dividing by 0 as well, isn't it? Because you have a 0 on bottom again. So this one, it wouldn't spike up. You wouldn't have a vertical asymptote as you approached x equal to minus 5. You would literally have where the curve is coming along, but then there's this hole in the curve. Okay, right there. All right, so putting it all together, I hope you can see that that gives you a very good idea what the graph looks like. So let's make some room and make the graph. So at the bottom of the screen, let's see if we can trace this guy out. And let's do it in, we haven't used green yet. We'll use green. All right, so we'll make some axes. And we have a 0 at x equal to minus 1. So let's go ahead and make some ticks. So, all right, so minus 1. So let's put a graph, a dot at minus 1. So there we go. There's a black dot. See that? That's also the x-intercept. And then the y-intercept, 0, 1/6. So something like that. All right. And then asymptotes at x equal to minus 2 and minus 3. Maybe I can put a blue, something like that. There's an asymptote. And then another one at x equal to minus 3. All right. And also y equal to 0. So there's our horizontal asymptote. And then we also know that as we get close to, or not close to, but as we're far away from the origin in both directions, the function goes to 0. Okay. So now, for the rest of the graph around the asymptotes, you might want to plug in some other points. So, for example, for let's try something between minus 2 and minus 1. So something like minus 1.5. Okay, that's going to give you looking at the function, the factored form of the function, let me circle what I'm looking at right here. So just give me the sign. So if I plugged in minus 1.5, the top would be negative, the bottom would be positive. So I'd have a negative value. Okay, so that means that the graph is going to be spiking down like that. Okay, remember that the minus 2 has to be an asymptote. So we know it's got to go shooting up or shooting down. All right, now likewise, let's now do in between minus 2 and minus 3. Let me label the minus 3 there. Okay, so how about plugging in minus 2.5, just getting the sign. So we know it's not going to cross the x-axis. Let's just see if it's above or below the x-axis. So minus 2.5, the top would be negative. The bottom, I would have a negative times a positive, so that's going to give a positive. So it's going to be something like this. Let me switch that to green. All right, so there you have that part, and let's keep going. Now for the rest of it on the other side of the minus 3, we're going to have the horizontal and vertical asymptote. Let's just see if it's above or below the y-axis, the x-axis. So let's try plugging in negative 1,000,000. The top, if I plugged in x equals negative 1,000,000, the top would be negative, the bottom would both be negative, so it'd be positive. So I'm going to end up getting a negative divided by a positive. So that means that the graph has to be something like this. That satisfies both the vertical and horizontal asymptote. Okay? So far so good? All right. And then if we were to plug in x equal to 1,000,000,000, the function is going to be positive on top and bottom. So the function is going to stay on top. It's not going to have any more x-intercepts, so it's going to eventually come down and get closer and closer to the x-axis. Okay? So this is not, I'm not saying that I have every, the curvature, I'm not saying I have everything perfect, but this is a rough sketch that is accurate of what this graph looks like. Okay, and all of that material, zeros, intercepts, vertical and horizontal, x and y, and then vertical and horizontal asymptotes, holes, long-range behavior, those are all things that help you to see what the graph looks like. Okay, now we can also go in the other direction, meaning what if you had a graph and you wanted to know what the equation, what the rational function was. Okay, let's do an example of those. So let's make a plot. So we'll make an x-y axes again, and let me put some numbers and we'll see how this goes. Let me try again. Okay, so suppose that I had, let's say, I had maybe a vertical asymptote at x equal to 2. Okay, maybe I had a horizontal asymptote at y equal to 1, and maybe the graph was looking something like this red line. Maybe it went something like this, and then maybe it went something like this. Okay, so let's see if we can figure out the function that has that graph. So let's get to work. So using the same material, let me list them all again. So these are always going to be useful, or a lot of them are. Zeros, intercepts, x and y, asymptotes, holes, and then long-range behavior. Okay, so we have a 0 at x equal to 1. We have intercepts at 1, 0, and let's say 0, 1/2. And then we have an asymptote at x equal to 2 and y equal to 1. We don't have any holes. And then for the long-range behavior, as x goes to infinity, the function, let's call it y goes to 1. As x goes to minus infinity, y also goes to 1. All right, so for the holes, that's the easy, or excuse me, for the vertical asymptotes, we know that to have a vertical asymptote of y equal to, or x equal to 2, that means we have to have an x minus 2 on the bottom. Okay? Now for the top, one way to get a 0 at x equal to 1 is if when we factored it, we had an x minus 1 on top. All right? Now, we don't have holes, so we don't need to worry about that. Let's see. So we've taken care of the 0. We've taken care of at least the vertical asymptote. So let me put a check there. We don't have any holes, so we're good there. And we took care of the x-intercept. Okay, now in order to take care of the y-intercept, you could multiply what we have so far by a constant. Let's call it k, and that will not affect the vertical asymptote and the 0 that we've established. Okay, by adjusting that k, we can get the 0, 1/2 y-intercept that we need to get. Okay, so that one's almost done, so keep that in mind. Now, to get an asymptote of y equal to 1, all right, so if we were to plug in bigger and bigger values into our function right now, we would get x minus 1 divided by x minus 2. As x got bigger, that would essentially, the top and bottom, both of those parenthesis blobs would essentially be closer and closer to the same number. You can go ahead and try this. Take x minus 1 and x minus 2, and on your calculator, try x equal 1,000, x equal 1,000,000, x equal 1,000,000,000. You'll see that it keeps getting closer and closer to 1. That's because as x gets bigger, the minus 1 and the minus 2 are essentially irrelevant. They're not making much of a dent because x is so big that the minus 1 and the minus 2 just make a very small change. So if you were to ignore that, you can see that you basically have x over x. All right. So this function goes to 1. So in other words, it'll go to, if that goes away for big X, what I have so far is going to go to k. Okay, so we could set k to 1. That would give us the long-range behavior, but it wouldn't give us the asymptote. So another variable, another way that we can tweak things is let's add another constant. Let's call this one c. Okay, we now need to adjust k and c so that we get the correct intercept and we get the correct long-range behavior. Okay, so focusing on this box, Okay, let's try plugging in those situations. Let's try analyzing those situations. So if I had x going to a really big value, the box would essentially go to k plus c. Because remember, the fraction, the x minus 1 over x minus 2, that goes to 1. So all I have left is the k and then the k plus c. So k plus c, we need that to equal 1 to get the long-range behavior, right? Okay, now let's try to get the y-intercept. So if I plug in 0 for x, I will get, on top, I'll get minus k, and on bottom I'll get minus 2 plus c, and that has to equal 1/2. All right? So there you have two equations, two unknowns. Solve those. Replace k and c with their correct values, and lo and behold, we've actually taken a complicated rational graph and got the function. And then we'll check, of course, but isn't that cool? So let's go ahead on the left side. I'll go ahead and solve this. So let me copy the k plus c equals 1, and then on the bottom one, let me first get rid of the minuses, and then let me double everything, so that'll give k plus 2c equals 1. So the only way that can be true, if I subtract the top equation from the bottom, I'll get c equal to 0 and k equal to 1. All right, so putting that in our equation, so the c goes away and the k is 1, so I guess that goes away. So it turns out it just was x minus 1 over x minus 2. Let's see if that works. So looking at it, it's got the correct vertical asymptote, it's got the correct long-range behavior, the zeros. All right, now let's see if the signs are in the right place. So if one last check you could do is, for big X, I have to have a positive value. Okay, so plug in x equal to 1,000,000, you'll get, let's see, you will get, yes, something bigger than 1, so that checks out in the first quadrant region. For x equal to a negative number, you have to get a number less than 1, so let's try plugging in x equal to negative 1,000,000, and that'll give you a positive number. So that'll be something, and it'll be less than 1. So it looks like everything checks out. All right. So that's an example, and I agree. There's a lot of stuff going on here, but that's the way you can deal with rational function graphing in both directions.